Welcome to Microcontroller Circuit Forge. This is lessons on how to build a microcontroller development board using datasheets. I'm your host, Veda Prakash. So, what you will be learning if you take these lessons: how to choose a microcontroller and how to understand it, power supply and clock designs for the same microcontroller, schematic designs, how do we build schematics on those microcontroller, programming interface for that particular microcontroller, reset and programming circuits for the microcontroller, general purpose I/O and headers for the microcontroller, and finally we'll be finalizing the schematic for the same microcontroller. Then we'll be moving on to PCB layouts. How do we place components for that particular microcontroller, PCB routing and grounding of the same, then exporting the microcontroller Gerber files, PCB Gerber files, and other details so that FabLab can manufacture it. So what is the objective of this particular course? So the objective is we need individuals to design and build their own microcontroller boards by demystifying what a microcontroller chip integration is. How do we analyze data sheets? How do we design printed circuit boards? And the power management for the microcontroller. So this we'll be dividing it into 10 different chapters. The first chapter is on how do we choose microcontroller and understand that same microcontroller. So when we talk about microcontroller, what are the features that we are looking in? Let's say I need a basic 8-bit microcontroller. That is the first feature. I require at least 8 bits. It should have pulse width modulation, I2C, USB programming without external chipset, UART or serial peripheral interface, timer. Let's say we want a bit advanced microcontroller, capacitive touch, and what's more fancy than glowing a NeoPixel in varieties of colors, right? So let's say I need all this in the development board that I'm looking forward for. So are there any boards? Yes, so this particular criteria might be fulfilled by many microcontrollers. Here we'll be looking at a particular microcontroller called CH552G. Because of its cost, this is less than $1 or within 50 rupees Indian. So a low-cost microcontroller, basic microcontroller, which uses the core which is there for many years. So this is the entire features of that particular microcontroller. So what it has regular pins for digital input output, timers. How many timers do we get? We get 2 timers on this. Timer 1. Where is timer 1? We have timer 2. I can see that directly here. Then timer 2x, right? So there are 2 timers in this. Then we have a serial peripheral interface, that is the chip select, MOSI, MISO, and clock. PWM, we get 2 PWM, PWM1, PWM2, and their mirrors. UART, again 2 UARTs, TD, TXT, RXT, TXT1, RXT1. Then our interrupts, we get 2 interrupts, 0 and 1. Touch, we have total of 5 touch pins. USB, direct USB without any other chipsets like CH340C, and unlock to digital converter for reading analog values. right? Other than that, in USB we have other details as well. USB 1, USB 2, which are used for if we are mapping on USB-C. Then if you want specific power considerations to be taken into, then VBus 1 and VBus 2 works, and CC1 and CC2 works as negotiations, right? This particular microcontroller comes in an SOP16 package with these dimensions, right? One thing that you need to note is this is a specific microcontroller where GPIO or the pins has the lowest priority, right? That means all other functions takes priority when compared to its intended digital input output. So you have to look it from the perspective of left to right. So for pin 3.2, analog read is first, then it looks at voltage on bus, right? Specifically for USB-C communication, interrupts, then the UART, then comes our pin or GPI. So that's how it has been designed. So how do we read a data sheet? So let me show you the data sheet of this particular microcontroller. Give it a second to open. So we'll begin with the section of reading the data sheet. So here I have pinned a data sheet, which is again I've opened in another window. This is 8-bit enhanced microcontroller CH552 or 551 by WCH. So what is CH552? It is an enhanced 8051 core microcontroller compatible with the microcontroller 8051 instruction set, right? And almost 80% of its instructions are single cycle instructions. That means it runs 15 times, 8 to 15 times faster than the standard 8051. This also supports 24 megahertz clock frequency. It has built-in 16K or 16 kilobyte program memory, which with 256 bytes internal IRAM and 1 kilobyte internal XRAM, right? So it also has inbuilt analog to digital converter, which we also saw, touch key capacitance detection, 3 set of timers, signal capture, PWM, 2 UARTs, SPI, USB device control, and full speed transceiver and other function modules, right? So this is what it contains. That's what we saw. This has internal oscillators. It has internal LDOs. We need not use external LDO. LDO is low dropout voltage regulator, right? It has watchdog reset. It has power on reset, right? Internal oscillator with multiplier so that we get uh, clock cycles even higher than 24 kilohertz megahertz. Sorry. Yeah. So what should we be taking away from this microcontroller datasheet at first glance? So we need to note this particular things down. What is the microcontroller core that we already saw? It is 8051 core. Voltage recommendations, that we'll look at it right now. So for voltage recommendations, usually this would be in parameters, right? Absolute maximum ratings. So this is the voltage. VCC is maximum of 5.8, so we cannot exceed 5.8 volts on VCC. and a minimum of minus 0.4. So voltage on USB pins should not exceed uh, VCC plus 0.4. That is, it cannot exceed 6.2 volts if maximum VCC is considered as 5.8. Other pins. So voltage on USB pins should not exceed voltage 3.3 or 3.3 volts plus 0.4. That should not exceed 3.7 volts at any point of time. Right? Here they have given electrical characteristics which are measured at 5 volts VCC. So when we apply 5 volts as VCC pin gets typically 5 volts, or because there would be slight variation, maximum 5.5 or minimum of 3.7. Right? Internal load LDO, which would supply voltage 3.3. If I have minimum of 3.7, it gets 3.14 volts. 5 volts, it gets 3.27 volts. 5.5 gets 3.4 volts. So if I select 24 megahertz, then the chip will be consuming at least 8 milliamps when it is working, right? If it is working at 3.7 volts, if it is working at 11 volt, 5 volts, it will consume minimum of 11 milliamps, right? Similarly, we have measurement for different kilohertz, right? If it is on sleep mode, then it consumes 0.1 to 0.2 milliamps of current. Let's say this is all this are for internal clock. I say I go with external crystal clock. Then the sleep cycle will be put on 0.08 milliamps, that is 8 nanoamps, right? ADC operating current up to 800 microamps, comparator module up to 500 microamps, touch key capacitance up to 250 microamps, input low level voltage 1.2 volts. So it would have input, basically what input low level voltages. If it gets below uh, zero point 0.4, it might not be able to measure high voltage, so it would be VCC plus 0.4 volts, right? Similarly, we have input current without pull down resistors, with pull down resistors, things like pull up resistor, all these values. These are the electrical characteristics or the power requirements. We'll get into it again in a minute, but voltage recommendations, operating voltage, we have multiple operating voltages for this. Voltage regulator, this is internal. Clock, we have option for both internal and external. This works on both micro USB or USB 2 and USB 3, USB-C. It GPIO pins, as we saw earlier, uh, it has 12 GPIO pins, but 10 of them, let me go back and show it to you guys. Just here we have 1 2 3 4 5 6 7 8 9 10 11 12 GPIO pins, out of which 2 are recommended for USB connections. So practically we can use any time 10 GPIO pins. So after that, we will look into peripherals. As we saw, it has multiple peripherals, UART, touch. I did not say I2C on the datasheet, so but I2C can be implemented in software by bit packing, right? But it has SPI communication and various other ways. Memory, we saw ROM memory, it had 16 kilobytes, data memory around 1 kilobyte, RAM around 128 bytes RAM and 1 kilobyte of accessible RAM, right? Number of ports exposed are 2, non-exposed another one. So in exposed as well, not all pins are exposed, so we need to be very specific on those pins. So pin configurations, here are the pin configurations. To be more specific, let's see here. So this comes in varieties of packages and varieties of pin configuration. So the other microcontroller CH552T, this is thin shrink small outline package, which is TS-SOP20. So it has 20 pins, out of which 2 are power pins and 1 is ground pin. So that makes it 17 pins exposed as GPIO pins. So 15 pins can be accessed as IO pins, leaving 2 USB pins. SOP16, which is generally common and is easier to solder. This is CH552G, which has 16 pins, right? It has a small outline package, which becomes easier for us to even handle, right? So SOP16 is what we need to concentrate here. So this is how many of the microcontroller pin definitions would look like. So here 15th pin is VDD, 16th is 3.3 volts, right? 14th is ground. We have 6th pin as reset, 9th pin as port 1 first pin, 2nd pin as port 1 fourth pin, 3rd pin as port 1 fifth pin, 4th pin as port 1 sixth pin, 5th pin as port 1 seventh pin, 8th pin as port 3 zeroth pin. So wise, right? What we need to concentrate other than that is other function names, right? What are those each pin capable of? So we need, if you, we can look at this particular pin definition as well, but we have clearly defined that in this particular diagram, right? If we know this, then most of the things are covered there. So we know that number of ports, pin configurations, so we are clear on those. So what does this contain, right? As I'm reiterating, and you might feel that this is again reiteration. 16 kilobit of ROM, which is iFlash, data flash of 128 bytes, iRAM of 256 bytes, and XRAM of 1 kilobyte. Timer, 2 timers, 3 timers, timer 0, timer 1, timer 2. Timer 2 has captivating or to be using the specific language, it has capture input on input 1 and 2 of timer or counter 2, right? So it has 2 timers. So here again we have timer 0, timer 1 is somewhere, timer 2, timer 2, things like that. 5.1 pin is timer 1, but that is not available in our package. So you need to understand there might be some pins which are not existing, and that might have its own values. For example, CH552G has this clock input, external clock input on no pins. If you select CH552T, then you could have given external clock input on 17th and 16th pin. So we have to use internal clock for this, or internal crystal. Hang on. So again, we have looked at the features of this chipset, and no need to visit it again. Okay, this is an important topic. Block diagram. So before we develop any microcontroller development board, we need to understand what that development board should contain. So the development board should have a way to get its power. It, here we are making it USB, right? Which would be the power from the voltage from the USB would be transferred to the LDO, internal LDO of the microcontroller, which would supply all the functions of microcontroller, right? The USB pin will also contain the data pins which would be sent to the microcontroller. So we need to have a way to reset the microcontroller. We need to configure the microcontroller's clock if it is external. Here it would be internal, so we can do it via software or basically the bits for that particular clock. Then we have multiple peripherals, UART, SPI, I2C, touch, timers, things like that, right? GPIO, analog input, timers, interrupts, which we can use on general purpose IO. Then we should also configure some power pins so that we can power other projects from it, right? So this is the block diagram. So this is how I had thought to build. So we'll be building each and every block separately, right? There might be some combination of blocks when it comes to microcontroller schematics and on PCB, but we'll be looking at each and every section. So this becomes our basic building block from now on. And this particular diagram would be referenced multiple times along with the data sheet in order to come up with final schematic. So that ends chapter 1. Before we move on to chapter 2, I want to just recap. Chapter 1 we discussed on how to select a microcontroller by looking at the features that we require. Then we saw into the power considerations. What is the minimum operating voltage? What is the maximum operating voltage? Right? What are the different power variations for the pins? Right? Then we saw peripherals, how to what peripherals it has. Would that be helpful for us? Things like that, right? And that's where the chapter 1 ended. So in the next video, you'll be looking at chapter 2.